Okay, so in this section, I want to go into more detail about exactly how you prove a sequence converges to a limit. Okay, this is one of the most fundamental types of proofs you'll have to do with the definition of convergence. Well, actually, yeah, I mean, it's good practice to understand the definition. Okay, and you'll have to do this more in the future. So I want to actually give you a really precise idea of what a proof of that should look like when you write it out formally, right? Instead of just like with pictures and stuff like that. Um, First, the way I like to, so this is our question, right? How to show, oops, that the limit, this is another notation, right, for saying that a sequence converges to a certain number, is saying limit of Sn equals S, not just the arrow. So how to show that the limit of a sequence Sn is S, right? Obviously, without more information about what Sn is, we can't really do anything. But I want to tell you about what the structure of these kinds of proofs looks like in general for whenever you try to do something like this, okay? The way I like to describe this is that it's a little bit like a game, okay? And I like to sort of pretend that it's like a game you're playing with the devil, okay? Because, you know, it's like your opponent in this game plays perfectly. You have to imagine that your opponent knows everything and can instantly, you know, make the best move possible. So you have to plan really well. Okay, so this is how the game works. So I call this um, the proving convergence game. Okay, so here's a little schematic. This is you. Okay, this is you. Okay, maybe you have glasses. I have glasses. So that's you. I don't know. All right. All right, and then here's the devil, nasty guy. Okay. Right. So there's the devil, and so you claim this is how you start the game. You claim Sn converges to S. Now the devil, what he's going to do is he's going to pick epsilon. So put this in red. Okay. So now what you have to do to respond, oops, what you have to do to respond is you have to give capital N. Okay? And then what he's going to do is he can pick a little n after that. Actually, let's put this in a nice green color. Okay? That's a nasty looking n. So you pick capital N. So you pick a limit, okay? And then the devil will pick epsilon, and he's going to make it as hard for you as possible, right? Then you have to pick capital N, and then after that you have no control, okay? It better be, so basically, and then at the end, right, what we check is Sn minus S less than epsilon. That's what it comes down to at the end, okay? The absolute value of Sn minus S. Is that less than epsilon with these choices, okay? So he's going to pick a small epsilon, probably. You have to pick a pretty big n, and it might depend on what epsilon he gives you, right? So he'll give you the epsilon. You pick n, possibly depending on that epsilon. And then you have no control. He'll pick a little n. And if there's any value of little n bigger than, so the rule obviously is that the little n has to be bigger than the capital N, right? But if there's any value of little n bigger than capital N, he's going to pick that any value where this is not true, right? Any value where the sequence is too far away from the limit, he's gonna pick that, okay? So like if you chose the wrong limit at the beginning, for instance, then he could pick a certain epsilon such that there was no value of capital N you could pick that would prevent him from being able to do this, right? So this is kind of how the game works. So the reason I do it like this is to really emphasize to you what you have control over and what you don't have control over. When you try to prove convergence, okay, you should not imagine yourself as having control over epsilon or little n, okay? Those things are out of your control. You're supposed to let them be anything, okay? The things you do have control over are the value of S you pick, which should be easy, obviously, and then the value of capital N that you pick, which is a little bit harder, all right? So this is the game, okay? I'm gonna, unfortunately, have to erase this beautiful artwork now. And so let's look at an example of this in action, right? Goodbye. Okay. So, oh yeah, let me just erase more of this stuff. So let's actually just, yeah, erase all this. Now, okay. So let's look at an example. Prove rigorously that the limit of, let's use, I'll use the book's example here. The limit of 3n plus 1 over 7n minus 4 equals 3/7. Okay, so looking at this expression, if you didn't know the limit beforehand, a common way of figuring these kinds of things out is when you have a quotient of two polynomials in n or something like that, or generally two expressions in n, you kind of look at what are the biggest terms on the top and the bottom and figure out how they compare to each other. So in this case, the biggest one up here is like 3n, the biggest one down here is 7n. These constant terms end up not really mattering. And so then if you just imagine taking the quotient of 3n over 7n, you'd get 3/7. So that's basically what it tends towards, right? So let's start the proof here. The beginning of this proof always will begin with this. Let epsilon greater than 0, okay? Always. When you're trying to prove convergence, always, just without even thinking, write down let epsilon greater than 0. Always, okay? Because you can't choose epsilon. It's just there. Now is the part where we describe a choice of big N. Okay, so it's kind of like the devil handed us epsilon and now we have to strategize, okay? So this is where we do scratch work. Right, let's think about our goal, okay? What is our goal? Our goal is to pick capital N such that for little n larger than capital N, the distance between this number and 3/7 is less than the given epsilon, right? So let's write down what we want. We want 3n plus 1 over 7n minus 4 minus 3/7. So this is our goal. We want this to be less than, less than epsilon, right? So let's kind of simplify the stuff in here. Well, the book did it for me. I'm not gonna. So looks like that all simplifies down to 19 over 7 times 7n minus 4. We want that to be less than epsilon, right? So, okay. One way to do this, like if you just look at the expression in here, right, you can kind of see that this whole expression is something that, which first of all, it's positive for all values of n, actually. Even when n is 1, this is positive. So you can actually just like kind of ignore the absolute values. They don't end up mattering. Okay, so we want 19 over 7 times 7n minus 4 to be less than epsilon. Now, the idea is like, well, we need to come up with a condition on n. So you can kind of just like manipulate this almost as if it were an equation, right? To solve for n, basically, solve for n. Okay, so let's just do that, right? So we could multiply by 7, divide by 19. So you need, and then let's reciprocate that. So we would get 7n minus 4 is greater than 19 over 7 epsilon. So I did a couple steps in a row there. I just moved these constants over, and then I took 1 over both sides. Notice that the direction of the inequality flipped when I did that. When you reciprocate both sides, the direction of the inequality flips always. And it wouldn't make sense if this was still pointing the other way, because we're supposed to find a lower bound on the values of little n, right? We want to find a capital N such that something is true when little n is bigger, not when little n is smaller, right? So we want to see that little n has to be bigger than something. So now just like, move stuff over. So we need n to be greater than 1/7 times 19 over 7 epsilon plus 4, whatever this is, okay? So if you reverse this, all of this logic is reversible, basically. What we found is that as long as little n is bigger than this expression over here, this thing, which is the ultimate goal, will actually be true. So basically what that means is that we could actually take this to be our capital N. So let's see. This can be capital N. Now I want to warn you, okay? This technique does not usually work. Sorry, not, well, really this part. Okay, normally the things you're dealing with will be complicated enough that you actually just can't solve for n, okay? So we'll talk about that more later, maybe in the problem session corresponding, the discussion section corresponding to these lectures. I'll show you there are tricks. So when this happens, you use estimation. Oh, that's really bad. Bad handwriting, sorry. Well, I won't write it, but you just have to, there's sort of a toolkit of little tricks for manipulating inequalities. And a lot of it involves estimation, using the triangle inequality, all sorts of stuff like that. And sometimes you end up having to pick capital N to be bigger than like some finite collection of different expressions or something like that. Okay, you can't solve for it exactly, but you don't need to. But we'll talk about that more later. In this case, we could, which is fine. So let's take capital N equal to 1/7 19 over 7 epsilon plus 4. Okay, then here you basically insert a reversed version, right? So then you'd say let little n be bigger than capital N. Then you use basically a reversed version of these steps, and you'll end up concluding that, so then 3n plus 1 over 7n minus 4 minus 3/7 is less than epsilon. And that's all you need to do. You've won the game, okay? No matter what epsilon you were given in the beginning, you were able to pick this capital N based on that epsilon, so that no matter what little n gets picked after that, this statement is always true. Okay? So that's all for proving convergence. There will be 2 more examples that I want to go through about proving things when you assume something converges, and also proving divergence. Okay?